Good afternoon, everyone. This is Amit Gaurav, and I'm a principal engineer at Dell Technologies, and I'm part of the team that manages the authorization, authentication, identity mapping of users at our product PowerScale, which was formerly called Isilon. And for those who do not know, the PowerScale is a scale-out NAS solution for the unstructured storage with its scale-out architecture and a single namespace across all the nodes of the cluster. It provides customer a real data lake that can scale up to like petabytes in capacity. Every PowerScale cluster node consists of, in fact, contains our proprietary OneFS operating system, and that hosts a distributed file system, and that provides a unified view of all the files that are hosted in the file system to all the applications that are running inside the cluster. Our product PowerScale also has a robust support for multiple protocols, and that's where you could see that a lot of our customers, they actually are accessing our cluster from SMB clients, the NFS clients, FTP clients, HTTP clients. And we are proudly support a lot of protocols as part of our product. So naturally, as part of multi-protocols, we do support a lot of multiple external authentication providers too. So naturally, users that are connecting to our cluster, they are connecting from either, in fact, they are configured as part of Active Directory, or they could be LDAP user, a NIS user, or they could be like local users like root or admin. And it is imperative that those users which are actually trying to connect to our cluster, OneFS needs to facilitate authentication for them. So OneFS does not authenticate those users by itself because they are not OneFS users. So what OneFS does is that OneFS facilitates authentication with the external authentication providers. So if they are Active Directory user, so OneFS will get the credentials from the user and will act as an aqueduct to send those authentication information to the Active Directory, which typically happens in an LTLM authentication, and the actual authentication happens inside the AD domain controllers, and then whatever the response is there, it will be returned as per to the user. And if the authentication is successful, very well, the user is allowed access, otherwise the access is denied. So in order to ensure that OneFS can perform authentication or user queries for all the clients that are connecting to the cluster, OneFS needs to maintain a consistent communication with the external authentication providers, which means that each of the OneFS or the PowerScale cluster node is connected to the configured external providers. So if it's the Active Directory, it's actually connected to the Active Directory domain controllers. If it's LDAP, it's connected to the LDAP servers. If it's NIS, it's connected to the NIS servers, which is fine. For the purpose of this session, we'll be mostly focused on the cluster connection to the Active Directory servers, the Active Directory domain controllers, because that is where the DCRPC thing actually comes into the picture. That said, this session is about making the DCRPC calls from each of the cluster nodes to the Active Directory time-bound, because right now they are not, they have never been time-bound. They are synchronous in nature by default. So this presentation is specifically about a specific use case and a specific problem that we faced as part of our communication with Active Directory, and how did we solve that particular use case. And this session is about that journey. So before we actually dive further, let us first understand what exactly a DCRPC is for the uninitiated. So DCRPC is, as the name suggests, it's the abbreviation of Distributed Computing Environment Remote Procedure Calls. It's actually an implementation of the remote procedure call technology, and it was developed by the Open Software Foundation. I think it's also called the Open Group. under the BSD license, and it's primarily used for the using the services of mostly the Windows, kind of taking out the services of the Windows like the Active Directory, or in fact you can actually make your own server that utilizes the DCRPC as a protocol. So what happens here with DCRPC is that a user sitting on a client can actually send a remote call to the server, and it does not need to know the intricacies or the internal remote communication involved as part of that particular call. Just like a normal local procedure call, caller will have to wait for the call to complete, and they will not be returned, or they will not have any response unless and until this whole operation is complete. Naturally, for a local procedure call, you don't have any issues because it's local. But for a remote call with DCRPC, all the internal remote network-related intricacies, all the communication between server and client is actually masked to the caller, and it's actually transparent. So it's more or less, from a caller perspective, it's like a local call, but indeed it's not. So how does DCRPC does that? So basically it divides the call into two parts, the client call and the server call. The client call actually implements the client part which is used by the client application to invoke a DCRPC call, and then the server part which the server application actually implements. So what happens internally is that a client invokes a DCRPC call, it goes into the DCRPC library, the library encodes the call, in fact extracts the arguments and then the call name, and that encodes the call into different network packets, and then it sends the call to the server. Now what the server does is that the server takes the call, it sends that call to the DCRPC library of the server, it decodes the call and the arguments and sends the information to the server implementation of the call. And as and when the call finishes, it returns back the response using the same channel, the same communication model to the caller. And then when the caller gets a response, the call is completed. So note that the thread actually is blocking till this whole period of time. It's like a local call. The message transport between the server and client can be SMB, HTTP, or you can make your own also. So that's what primarily DCRPC is, and that's what is, it's actually a much deeper, but for the purpose of this session, I think this information should be sufficient. And looking forward to the issues that we have with respect to this DCRPC. So the issues are pretty straightforward, which I think I have said earlier also, that the calls are synchronous. The calls here, they actually, in fact, the DCRPC, the design of the DCRPC was done with the assumption that the calls will be blocking, and every thread that actually performs a DCRPC call will be blocking in nature. It's a paradigm. It's a paradigm perhaps because it's an old library. Perhaps I think it was developed in early 1990s, and then it was not changed after that. But we cannot change that. But the thing is that some of the inherent issues still remain with DCRPC. The first one is like remote calls are error prone. Like you cannot just guarantee for a remote call that it will be completed in this period of time. Because the network can be flaky and the network is not reliable. The other issue is that in case of remote calls, in case of DCRPs, the server can act crazy. Obviously a good server will always behave in a good way. You actually send a call, it will return back properly, but a crazy server, due to some of the other issues, they can return some arbitrary data, or they may not honor the request. So what will you do in that case? And there's also a possibility of a bug in this whole path, in which case you should be resilient enough to come out of that particular thing, which I think we have had issues with that, but effectively we want a guarantee, a simple guarantee with DCRPC that any call that goes through DCRPC from our cluster node to Active Directory should have a reasonable SLA associated with it. But with the issues that we have with DCRPC, this is not possible because of its synchronous nature, and it's not really handling the bad server or the bad network capabilities. So the thing is that it's not I mean, these issues which I'm actually talking about, they are not really like recent issues. So, I mean, DCRPC is old, and we are actually using DCRPC for a pretty long time. The thing here is that, I mean, there are like a lot of escalations that we have had as part of our product, and wherein the customers they have complained that your authentication service is not really responding. It's actually stuck. And as part of our core analysis and log analysis, we saw that, oh, there is one call that's actually stuck in DCRPC, and it's actually waiting for the Active Directory. And we don't know. I mean, when we actually looked at the call, I mean, sometimes it used to be like 5 hours, 8 hours, it's actually waiting, and then it's not getting any response. Obviously, I mean, it was a network blip, and then it could be a server-related issue wherein the server did not respond back. But we have seen these cases wherein a call is stuck for a long time, and I think in one of the cases wherein there were 600 threads that were blocking, that were like, it was a cascaded blocking thing, and then they were blocking on this particular thread that was blocked on Active Directory. Why? Because this particular thread has some weird lock taken, and then all the threads were blocked on that lock. So the thing is that these cascaded issues, they have been there as part of our product with DCRPC, but then over the period of time, the number of escalations started rising, and then, I mean, we actually thought that we should do something on our own and should not rely on the external network or the external Active Directory for this resolution. Because whenever that happened as part of customer, we used to tell that there might be some issue with your network, and indeed a lot of times it used to be some issue with their network, some flaky network issue, and then it used to resolve on its own. But then things started rising, the escalation started rising, and then we thought that we should have some solution on our own. And we do have a solution, and this actual session is about that journey. So before we go further, let's talk how exactly we use DCRPC in our code. So basically, 1FS leverages DCRPC to communicate Active Directory as said. It uses DCE 1.1, the likewise implementation, which is actually what this product is. It uses it for the regular services, DCRPC services like netlogon for the user authentication and the DNS queries, the LSI-RPC for the user group information, and SAMR for account creation. So they are very popular DCRPC services exposed by Active Directory. The communication with the Active Directory is through the SMB transport, which means that the
With the first question, what authentication are you using there? Kerberos or
we do support, we support Antilam also and the Kerberos also. So this, oh yeah. So the question is, what kind of authentication do we support? So we support NTLM authentication as well as the Kerberos authentication for Active Directory. In Kerberos authentication, we do not need this DCRPC because the authentication is done at the client level only. But in case of NTLM authentication, which a lot of our customers they still use, we do need a DCRPC to perform this authentication with the Active Directory.
and when you connect to SAMR or LSA, how do you authenticate against DAT then?
So SAMR is for like machine account creation and modification.
Yeah, but do you do Kerberos there?
Yes.
Can you repeat the question?
Oh yeah. Yes. So the question is that when we actually use SAMR, do we use Kerberos to connect to Active Directory, right? Yes. Yes. When we use SAMR, we do use for connection of our cluster node with the Active Directory. You can say that process is called the machine joining with the domain, right? So that happens using the Kerberos only. That's the internally it actually uses Kerberos.
Timeout actually runs over assembly, and assembly, the connection over assembly, that connection is established using Kerberos. The machine account is authenticated using Kerberos, and the assembly connection which uses the transport is authenticated using Kerberos.
So you don't do direct TCP.
No, we don't.
So yeah, with that said, the communication with Active Directory is through SMB transport. So that means that the DCRPC layer that we have actually communicates to Active Directory using the SMB transport, which is possible because Active Directory supports SMB as a transport for DCRPC. So note that in the diagram below, so we have this auth service that's going through the client DCRPC, and then our homegrown SMB client that is going to the server one. Looks pretty simple. Note here that this SMB client that we have, it's like a homegrown or locally coded SMB client. I mean, not that it's very difficult to do that, but it's actually used in later slides. So that's why the emphasis. For the purpose of our DCRPC issue, we have just two basic requirements. The one was that the call should not remain waiting forever, whichever the call is. Like if it's a network call, if it's a local call, it should not remain waiting forever. And in case of our escalations, we have seen that it actually remained waiting forever. And the second requirement is that a caller who is actually initiating the call, they should have the capability to time bound a specific call. They should have the capability to make sure that I want this call to be waiting only for like 1 minute, 30 seconds, 5 seconds, or 10 minutes. That SLA guarantee should be there for the purpose of this solution. And as I said before, the issues that are preventing this to happen are like the calls are blocking, and we do not have any immediate resolution for that. And a delayed response or no response can cause cascade delays because DCRPC has a lot of internal mutex logs. And they are like association logs, they are like association group logs, and then any thread can take any random log at any point of time. And if it's blocked, then that can cause cascaded block for any subsequent call that's going through DCRPC. We have seen that in one of the escalation that there are 600 threads just waiting, and threads use system resources. It's just wasteful to have those many resources just waiting for the response. And the fourth point here is that calls cannot be cancelled from within the DCRPC. So although DCRPC provides a functionality to cancel a call, like if you have a waiting call, you can actually cancel, but it relies heavily on the server. So what happens is that when you cancel a DCRPC call, it actually sends a request to the server saying that please cancel this call from your end and send back the failure to our end. So what happens is that server will cancel the call and then it will return back the cancellation status to the actual call that's waiting. And when that gets the cancellation error from the server, it goes back and then the call becomes cancelled. Naturally, that heavily depends on the server. Like this will not work if the server is unresponsive or server refuses to honor the request, which is what is happening in our case. Because as the next slide says that we do actually try to induce timeouts in DCRPC to see that what exactly was, can we have a solution inside DCRPC to make sure this works? But apparently, as said, it does not, because it relies heavily on a good server. And in our case, we have had timeouts because of unresponsiveness. So it's highly unlikely that the server will respond in our case. And that's why we needed a solution that will have functionality to cancel the call irrespective of whether the server is responsive or not. So we actually tried changing DCRPC to make sure that there is a separate thread that runs inside DCRPC, and it actually cancels the call. But the main blocking factor is that the call that goes out of the DCRPC is actually blocking. And the only way to remove that call, the blocking call, is to cancel the thread. It's anyway a POSIX thread. You can just cancel the thread. But that's disruptive. I mean, you do not want to cancel a thread. I mean, obviously in our architecture, we do not have a facility to cancel a thread. We do not support that. Personally also, I do not support cancellation of any thread. I mean, it should all be graceful. So yes, I mean, there was no guarantee with this approach that we'll be successful. We also tried asynchronous DCRPC. So DCRPC is synchronous as of now. Every bit and piece is synchronous. We tried to do asynchronous DCRPC wherein we tried putting an additional parameter as part of every call, every DCRPC call, that would return a promise, a so-called promise, and that will be kind of a, that will hold the future, I mean, for this particular call. So if the caller does not want a particular call to continue, if does not want the result, they can just cancel the promise. And that will internally go inside the DCRPC, and then it will be cancelled immediately. I mean, obviously, whatever DCRPC does inside, that's a separate matter, but what matters here is that the caller is freed and they can actually do whatever task they want. But the thing here is that upon changing DCRPC in an asynchronous mode, we realized that the changes are very significant. It's actually disruptive. It actually needed changes in the IDL, the interface definition language, which is a DCRPC compiler that generates the client and server routines. It actually had changes. It actually needed changes in that layer, and it also required a lot of changes in the message transport also, because we do not want a blocking call even with asynchronous DCRPC. Obviously, we want a promise for the outgoing call from the library also, and it required a lot of changes. And at one point of time, even after the prototype that was ready, we thought for a bit that maybe it's not the value that it intends. I mean, it's not providing the value that it intends to provide, because it's a huge code change, and we do not want timeout functionality to be accompanied by such large code change, because there are a lot of consumers of DCRPC in our, business unit, and all of them, they actually need to recompile their code. They need heavy testing to make sure that they are compatible with the new one. So they were very basic issues that we faced. Although MSRPC, the Microsoft-based RPC, they have actually changed DCRPC to, they have changed the ideal to create MSRPC that's asynchronous in nature. So, but then that's proprietary Microsoft one. So, we cannot use that in our BSD clients. So is there a way to meet the requirements without messing up with DCRPC? Yes, obviously there is. So the solution is right in front of us. That instead of changing the DCRPC, why not just change the SMP client that connects to the server DCRPC? Why not just add timeouts at that layer, right? The purpose of this whole session was that how exactly we started with changing the most complex library that we have had as part of our product, the most old library that nobody ever touches, and then slowly going ahead and then realizing that perhaps maybe we should not have done that, right from the start. So that assembly, the client that we have that's connected to the DCRPC, we can actually add timeouts at that layer. And the timeout information can easily be passed from a caller to DCRPC to this assembly client using a separate set of calls. You can easily create new data structures that can do that. So that's a pretty clean, that looked a pretty clean approach to all of us. And then we thought that perhaps we can go ahead with this. And that is where we started exploring that how exactly we can support a timeout as part of assembly clients, which should not be a very tough work to do, because we just needed to map every DCRPC call with every assembly client call. But apparently, it's not very straightforward, because every DCRPC call is not really mapped to a assembly call. In fact, every call, every remote call that one does, it actually maps to two calls. The one call is the assembly write, which actually sends the request to the Active Directory server, and then there's another call, assembly read, that actually tries to get response from the Active Directory server. But these calls happen only when there is the active connection. So for active connection, you also need to initially SMB, you need to connect, negotiate, session setup, and all those things. You need to do that beforehand so that you can actually perform a proper DCRPC call. In our case, for most of the scenarios, the SMB read never received any response. Like our cluster nodes used to send the SMB read call and then no response from the server. And then it just kept on waiting for like long period of time. So we tried to add the timeout at this layer, the SMB client layer, and you can see here the two calls, the SMB write and SMB read. I think, okay, so it might be in next slide, yeah. So you can see that the two calls, SMB read and SMB write, they have they actually they kind of make a single DCRPC call, and they can be, since they are network calls, they can be adjusted to make sure that they handle the timeouts. So in this diagram, I'm just talking about what exactly we did to support those calls. So whatever calls that actually came from DCRPC, we actually first, in the SMB client, we actually first put them into the pending send queue. Actually, we created 3 queues: pending send, pending response, and pending cancel. We first put the call into the pending send queue, and as and when the SMB write operation is completed, it will remain in pending send. And when the SMB write operation is complete, it will be moved to the pending response queue. And when the SMB read operation also gets completed, it will be returned to the DCRPC caller. Fair enough, this is a straightforward implementation. We added timeout in that, wherein we added another queue, pending cancel, and there's a separate timer thread that's running in the SMB client. What it does is that whenever there's a timeout and that's reached for this call, and the call is still in one of those queues, either pending send or pending response, it will be moved from those queues, and then it will be moved to pending cancel. And then a separate thread will look for items in pending cancel, and if there's an item, it will just cancel that call and then return error to the DCRPC. This is fair enough approach, and it kind of solved our problem because we have the timeout value and we can just tweak the SMB client to perform the timeout. And this is what it does in words. I mean, whatever I said, that there's one network call to send to the server, and then you just keep the call into the pending send queue, and upon timeout, you just move it to pending cancel. And same you actually do with the SMB read. And a separate thread will actually handle the pending cancel items. Obviously, this actually gave us added benefits. Like if there's a call that's cancelled here, we have the benefit, or we have the flexibility to retry this operation later, or retry this operation on a different Active Directory server so that it might succeed in that case.
Wait a second, you retry the SMB layer against somebody else?
Pardon the question?
You modify the SMB layer.
No, so if I read the question, listen the question correctly, so are you asking whether the retry happens at the assembly layer?
Yeah.
No.
Okay.
So this is just you can say aqueduct. So whatever call that fails, it will be returned to the DCRPC, and then from DCRPC it will return to the auth layer. It is the auth layer that's the brain here. So all the retry operation, whether to retry or not, or whether to retry on the same domain or a different domain controller, that actually is performed by that layer. So if we need a retry, that auth layer will initiate another call from DCRPC, and that will go here.
Cancel.
Yes.
So what happens to the response? For the read, which will either come in future or never come?
Yes, actually the next 2 points actually talk about that. So, so when we actually cancel a call, so as of now we do not send any cancel request to the Active Directory, the server, the domain controller. Which, I mean, theoretically we should actually send a cancel operation to the server saying that we do not need this call. I mean, we are no longer interested in processing the operation. So perhaps if you are actually trying to process this call, then you should not, and we should do that. But we are not dealing with the normal cancellation here. What we are dealing with is the timeouts, wherein the server failed to respond within a period of time, and hence we are dealing with this code here. So naturally, it is highly unlikely that server will respond to our call for this for the cancellation, and hence in that case, as of now, we do not send any cancel request to AD. But there is another case that arises, like what will happen to delayed responses. Like we have a SMB read operation, we are waiting for response, but then response didn't come, and then we had to cancel this call, and then the call was moved to pending cancel queue, and then it was cancelled. Let's say after 3 or 4 seconds, the call actually came to the SMB client, and do we honor that call? No, we do not honor that call. So that becomes a no op here. We ignore that response from the Active Directory. So if so your question was that if there is a response from the server for the SMB read call later than the timeout was, whatever the timeout was for the call, will it be honored or not, right? This one.
Let you finish your talk.
Okay. So yes, so delayed response will be treated as a no op. So finishing thoughts. So the thing is that what's special about this whole problem solving approach is that, I mean, as said, like we started with tweaking the biggest or the most complex chunk. We did spend a lot of, like, I think a couple of months fixing or modifying or tweaking the DCRPC layer, the complex layer, but eventually realizing that perhaps that's not even worth the effort. I mean, the amount of change that we are making in DCRPC and the amount of value that we are getting, it's perhaps not really useful. And that's when we actually decided that perhaps we should look into the areas where we can actually do it without really hampering the path of the DCRPC. And that's where this SMB client actually came into the picture. And this solution is more graceful, limited changes, and does provide the guarantee of having or finishing the call within a specific period of time. So yes, I mean, our learning with respect to these changes was that the ROI is important, and whatever change we are making, and it should provide the value, specific value that it intends to provide. And so yes. So with that, the presentation is over. Thank you very much for listening to this presentation. Any questions?
So in December, we often have problems with Kerberos libraries going wild and blocking for minutes and so on. Did you also see something like that? So where the Kerberos library would get stuck talking to the main controller?
Yes. So the question is, we have seen the Kerberos library also getting stuck, right? The Kerberos call, the KRB calls, the Kerberos KRB5 calls getting stuck, and they need to be handled separately, right? Yes, the answer is yes. We do have situations wherein the Kerberos library is stuck, mostly because of, I think, 2 reasons. The first reason is the server it actually chooses, it actually is unresponsive. It does not respond due to some network issue. And the second issue is that it actually caches some of the servers, and those servers are no longer running or no longer in operation. So we do have such issues, but they are not part of this path. So this will not solve the Kerberos issues. In fact, we have 3 different issues that are currently ongoing. One is the Kerberos issue, which we are trying to solve. The other one is the DNS. DNS calls are also synchronous, and they actually block. If obviously DNS calls are not really as impactful as these calls, because if one of these calls block, they actually block a lot of other calls. But DNS calls are like independent. So you can actually initiate a worker thread, and worker thread will initiate a DNS operation, even if blocks, that's like harmless. Like it's just one call that's blocking, and nothing else will happen to the rest of the process. But yeah, that's also one of the things that we are looking at. And
back to what I was asking, trying to understand the read, right? So you have these reads sent to server, putting it in that pending response, and let's say wait for X seconds, X 10 or so. And the pending cancel, you fail the RPC to the, or you fail the DCRPC
yes.
to the layer, and that might have read write logic. So what happens? So you already answered this part where if the read response shows up after a few seconds, you throw it away. Is there a hard limit on that? Is there like typical assembly clients will tear down the connection on a request time, right? Beyond 60 seconds or whatever that is within those times. So anything like that happens here after that point?
So the question is that. So correct me if if I'm wrong. So the question here is that if the response comes after a period of time and that kind of exceeded the timeout of that particular call, so what happens to that response? So do we have a hard limit to not honor that particular response which is delayed, or are we flexible enough, or is there any plan to handle such delayed calls also?
Not really, customer specific to you. I think you have a custom client here. You have a SMB client which
Yes.
is not standard or it's not Windows, right? So you'll have also a limit to which you're ready to wait for a response for a request and decide to tear down the connection, right? So maybe that's what I was.
So I think, Amit, the question is, so we have a timeout for DCRPC. So the question is, do we have a timeout for the SMB off to complete with the window roller? I think that's the question.
And when do you turn on the 445?
Yes. So is there a, so I think the question is, which I don't know the answer to, you might know. The question is, when we do an SMB call to the Active Directory server, if it's not doing DCRPC, if it's doing DCRPC, I assume that the DCRPC operation will get cancelled and those things will happen.
Yes, yes.
So is there something which is there a timeout specific to SMB? I think that's the question.
Yeah.
Yes, yes. So yes, obviously, yes. So there is a timeout. So the question is that, is there a timeout specific to the assembly client? So are all the timeouts associated with the DCRPC call only, or is there timeout specific to SMB client? Right?
Yeah.
Yes. So the answer is yes. There is a timeout. There is a default timeout specific to this assembly client. Which is, I guess, right now 300 seconds. That's 5 minutes. So if there is a call that is initiated from DCRPC and it has a timeout associated with that, that will take precedence and that will be honored. But if there is a call that's not from the DCRPC, this is our homegrown SMB client, so it's used elsewhere also. And it's part of a there are different consumers for this SMB client also. So if there is no timeout associated with that call, then by default, default timeout of this SMB client will be leveraged. And that's, I guess, by default 5 minutes.
But if you have a timeout on the SMB connection, on the SMB read request, why doesn't that ripple up to DCRPC? Because you have an old standing SMB read, that doesn't, then you see never the response, you never see a response to that. Why don't you just tell DCRPC after 5 minutes, hey, go away?
Yeah, but then it's okay. So the question is that why not use the timeout at the assembly layer, right?
Yeah.
And then after 5 minutes, just tell the DCRPC to just go away, and then the timeout has reached. Yeah. Yeah. So the answer is that putting timeouts at the SME client layer does not give the handle, or you can say the power to manage the timeouts at the caller side. The timeout for every call should be decided by the caller, right? Which is the DCRPC here, or which is the caller here. DCRPC is just a mechanism, but the user who is actually initiating operations through the authentication service, should have the power to decide that what exactly my call, how much time a call or how much time a DCRPC call should take. Obviously, the timeout here at the SMB client is you can say is that it's a backup plan. You can say that if there is no call associated with DCRPC, if there is no timeout associated with DCRPC, if there is a stray call that does not have any timeout, it should not be blocking SMB client forever, right? So that's a kind of a fail-safe mechanism inside SMB client so that none of the calls should block forever, at least in SMB client.
This would have solved your 600 threads for days.
Yes, yes, absolutely. So the question is that this should have solved the 600 threads waiting on the call. Yes, absolutely. Yes.
So the other thing is, I think that a single SMB connection to the DC can potentially connect multiple named pipes.
Very sure.
And this particular problem could be the result of a particular named pipe server hanging on that DC. So now, because of this, if you tear out the whole connection, it might be a little excessive.
SMB timeout is when you tear down the connection at 5 minutes, or you don't.
Correct. So you got this point.
Yeah.
Yeah. So
This one you want to learn about async RPCs, right? So I'm not much familiar with DCRPC.
This one.
So is that something relatively new? Is that something
No.
you put in our plan?
it has been there for. It's there the original DCR.
Yeah, so the question is that, is this whole thing new? So the answer is no, it has been for a long period of time, and that's what is also part of the problem, because when it was developed, everything was kept synchronous. I mean, everything was developed with the synchronous calls in mind, and that's what made it a lot more complex.
But if you had implemented this, you would not have seen this issue at all.
If you had what?
If you had support for this on your client side, assuming that Windows as a server has support this.
So the question is that if we had support for asynchronous DCRPC, we would not have this problem. Yeah, I mean, the answer is yes. I mean, if it's asynchronous, so there's a way to unblock the caller at a period of time, like after a timeout or whenever they desire. So if the caller can be unblocked, so yes, it's not an issue. And yeah, I mean, the only issue that we faced while prototyping is that it's very disruptive. So the thing is that it actually changes the compiler, DCE compiler, and to generate new CLI and the client and the server interfaces, it actually changes the message transport. So the DCRPC actually sends its encoded packet as part of SMB payload to the SMB client, right? That call, where it actually sends it to the SMB client, that cannot be synchronous within async DCRPC. That also.
TCP/IP transport, because I guess
Not SMB. No, so I think the other point is that even if you do the async, right? So what is async giving you? It's freeing up the thread. But at the end of the day, you still need to time out these async calls. Right?
So yes, I mean, that's how it is. I mean, rather than putting in efforts for asynchronous DCRPC and then doing months of testing to make sure that it works properly, I think we had to find another way out. Any questions?